Hello all, I'm Chinmay. I lead the Flutter engine and platforms team. I've been on this team since early 2015. Our team is responsible for writing and maintaining the platform agnostic core of Flutter. This includes stuff like rendering and runtime integration. I presented this talk at the Dash Summit held in October of 2022. This was a gathering of Googlers working on Flutter and Dart to share ideas and progress. Flutter is open source, and everything I present is and has been out in the open already. But hopefully, this talk sheds some light on how and why we chose to make the decisions we made and our outlook for the future. Having said that, the contents of this presentation are a couple of months old as I record this, and will be older still by the time you see it. With that in mind, I will try my best to describe the more evergreen aspects of Impeller. This talk is also a very gentle introduction to Impeller and assumes little to no rendering background. If, in the process of simplifying the concepts at play, I butcher some nuance, I offer my sincerest apologies to many folks working on Impeller who have to solve extremely complicated problems on a day-to-day basis. With that out of the way, let's begin. So, if this is the first time you're hearing about Impeller, and I wouldn't blame you if you hadn't, it is, after all, a somewhat low-level implementation detail in Flutter. What is Impeller? It is a new rendering engine for Flutter. It is built from the ground up on the foundations of consistent performance. I liken it to AOT mode for rendering. I remember a time very early on in Flutter when the release mode for Android used the .jit runtime mode. Remember, iOS can't do JIT because of App Store restrictions. The thought process then was that peak runtime performance could be obtained from the JIT model since it had profiling information available at runtime. But we quickly discovered that the performance of the first frame is just as important as that of the nth, even more so as it affects the out-of-the-box user experience. If we can only get adequate performance after caching and warming up, the user may just delete the application due to their poor first experience. We switched to AOT model with Dart, which has worked out really well. Impeller is the application of a similar thought process to rendering. For folks familiar with the internals of the Flutter engine already, Impeller replaces Skia in the tech stack. The Flutter engine still uses Skia for text layout and its abstraction over image codecs, but Skia no longer gets a graphics context when Impeller is enabled. Impeller itself isn't a wrapper over Skia and is architecturally dissimilar to Skia. Impeller is already used in production on iOS. I urge folks to install the wondrous application announced with Flutter 3.3. Already a few months old at this point and using an older version of Impeller, it is still a good showcase for Impeller rendering an application meant to push the boundaries of what you can do with Flutter today. We expect it to be feature complete on iOS by the end of the year, and I'm happy to report that all rendering operations, barring some corner cases, are covered now. We, as a team, discussed what Impeller 1.0 on iOS would mean, and I have a few remaining work items around better performance that we have added to a milestone on GitHub. Hopefully, by the time you see this, these have been resolved as well. So, why did we build Impeller? It is, after all, a rather severe undertaking. For that, let's begin at the beginning. I'd go back to May 2019. We had just released the Google Nest Hub, whose UI was powered by Flutter. The Nest Hub was a huge milestone, and for a few reasons. It was the first user of the Flutter engine's Embedded API. A non-iOS or Android use case, the platform-specific native components were written against a stable interface vended by the Flutter engine and written by a different team at Google. Use cases like Flutter on desktops, Raspberry Pis, and in-vehicle infotainment systems were enabled from the lessons we learned from this effort. It was also an extremely challenging launch, though. You see, Flutter used to be UI as code, but things started to change around this time. A lot of the most interesting elements of the UI were built using what we considered tools best used for offline prototyping or post-processing. Formats derived from a design prototype built in Adobe After Effects or SVGs with little to no optimizations applied. Tools automated producing rendering intent that could be extremely inefficient and hard to replicate in code. But when finding and fixing performance issues, we couldn't go back to the developer and offer guidance on how to fix their code because usually there was no code to begin with. And in some cases, redoing the assets was a no-go. A lot of the unfortunate kind of heroism went into shipping the Nest Hub, and the team knew we'd need to tackle a lot of challenges around rendering performance, and soon. Unfortunately, soon came a lot sooner. GPay was shipped with performance that many of us considered dismal. The same patterns we saw in the Google Nest Hub product were repeated and to extremes. For some folks on the team, each dropped frame hurt, and GPay was excruciating. On a personal note, as a Flutter superfan, I had to take a couple of weeks away from Flutter. This was very hard to do when I chose my bank because they used Flutter to build their mobile app. I just wouldn't access my bank account for a couple of weeks because I was on a self-imposed break from Flutter. In somewhat of a panic, we tried to offer solutions based on things we learned from shipping the Nest Hub, but those fundamentally didn't scale to mobile and caused their own issues to boot. Impeller solves more than just one class of performance problems, but the primary impetus for the project was fixing shader compilation jank. Jank due to shader compilation was always an issue, but we managed to work around it on a case-by-case basis, often using creative techniques in code to sidestep the problem. The earliest bug describing shader compilation jank I could find on the tracker was this one from late 2015, almost since the beginning of Flutter itself. Somewhat expectedly, in late 2020, the community noticed and called us out for it. This was presumably because of the prevalence of the same patterns the team noticed with Google Nest Hub and GPay. I alluded earlier to working on a short-term solution in somewhat of a panic. The shader warm-up approach was one such purported solution. The idea was that all screens an application could display would be rendered upfront, and the shaders generated from those runs would then be collected and packaged along with the application. At runtime, during application launch, the pipeline state objects from those shaders could then be precompiled to warm up the renderer. This has a few problems, some very obvious and others deceptively subtle. For one, there is additional burden on the developer to run through all the screens of their application. Packaging the shaders increases the application size as well. Also, warming up the shaders during application launch delays time to first frame. Also, the shaders are only semi-portable. So shaders collected on iOS may or may not work on Android, but they definitely will slow down application launch. In fact, due to differences in use of extensions, shaders collected on some Android devices would sometimes cause rendering issues or crashes on other Android devices. Looking on the tracker, I found this unresolved issue. Shader warmup was an ad hoc technique we built to fix issues in the Google Nest Hub, and it only worked there because of the architecture of the devices was so similar. Even when shader warmup worked, at best, you were trading one problem for another. As I said, we still had to process the package shaders at application launch. This would inevitably lead to delays in time to first frame. This user reports that their app sits on the splash screen for about 6 seconds on first launch, which is really poor first impression. Yikes. This is obviously a particularly extreme case, but I can say that most internal apps don't use shader warmup because of the negative effects on time to first frame, a metric that folks are particularly sensitive to. As you can tell, we were extremely frustrated by the status quo. All attempts at addressing the issue using existing components kept running into usability issues. In early 2021, we took a step back and said, if we had an ideal renderer, how would it work? We had some ideas, but we didn't know for sure. So we put our thinking caps on and embarked on figuring out a long-term solution for these and other problems. Faced with this daunting task, I particularly remember this nervous quip made around this time. There were a lot of failed prototypes, but from these prototypes, there were 3 promising approaches. Discussing the approaches in the failed prototypes is perhaps an exercise for another talk, but Impeller was born out of one of those prototypes. Of the other 2, one didn't solve all of Flutter's existing use cases. It works super well in 90% of the use cases with no way of addressing the rest. Making huge modifications to the Flutter API was already off the table. Another was perhaps too clever, and initially slow, needing significant time-consuming investments. It also needed more modern hardware. Remember, Flutter has to target devices that are sometimes really, really old and outdated by some standards. These devices typically only have OpenGLES 2.0 capabilities, but make up for about a quarter of all Android devices. Leaving these users behind is absolutely not an option. In discussing why Impeller doesn't work one way or another, it's useful to keep in mind the constraints on the available solution set. Impeller is very specifically built for Flutter's needs, and I'm sure it would look a lot different under a different set of constraints. It should also be rather obvious that any solution would necessarily also be one that the team could realistically implement. We are still a fairly small team with limited resources. So how does Impeller actually work? To understand that, we need a primer on how GPU rasterization works. Not to worry if you're a beginner to rendering, this is all something you'd encounter in an Intro to Computer Graphics course. As I hope you'll soon see, it's really quite straightforward. I like to jot things down on a piece of paper when describing simple concepts. I've attempted to do something similar here. Fundamentally, GPU rasterizers can only draw triangles. Everything else is an elaborate illusion. Rasterizers give you, the developer, an opportunity to run a tiny bit of code at specific stages in the rasterization process. These tiny bits of code are the shaders I've mentioned so many times before. These are like C functions, usually tiny but can get somewhat complicated. Vertex shaders, in blue, are run once per vertex. In the case of a simple triangle, 3 times. Pixel shaders, in yellow, are run once per pixel. In the case of this triangle, once per pixel that the triangle covers. Before these shaders can be used, the functions need to be compiled and linked into a program to be executed on the GPU. We call these programs pipeline state objects, or PSOs for short. Like any C or C++ program, compilation and linking is extremely expensive. All best practices say that this should be done offline at build time, or at least outside a frame workload. Unfortunately, due to the architecture of Flutter's current renderer, the optimum shader for a rendering operation is generated just in time, in a frame workload. Once the optimum shader and the resulting pipeline state object is obtained, however, it is cached. But this scheme leads to jank in cases where there isn't a pipeline state object. This is insidious since it affects first-time user experience. Triangles are fine, but let's attempt a different shape. Here is a totally valid way to render a circle using tools we just discussed. We draw 2 triangles with coverage enough to cover the entire area of the circle. For each pixel, we check to see if we are within the area of the circle. If we are, we shade the pixel. If not, we move on. Now here, like elsewhere, I'm glossing over a lot of things. It's a little bit more complicated than this because of stuff like anti-aliasing, but fundamentally, that's really about it. The key observation here, though, is that the shader is doing too much. It needs to reason about not only shading the pixel, but also cares about the circleness of the geometry. Not to mention stuff like anti-aliasing. If we had a different shape, say a square for example, we'd need a different shader. If we needed a different shading feature, again, we'd need a different shader. So hopefully you can see that this approach leads to a combinatorial explosion of shader variance needed. On the other hand, Impeller shaders can only shade pixels in a triangle. That's it. The shader doesn't need to worry about the coverage of the polygon. You can get away with just a single shader for each shading feature. But all shapes need to be expressed as triangles. Impeller does this using a separate tessellation or triangulation phase. Pixel shaders in Impeller generally do not modify coverage of the polygon. As with everything, there are exceptions to this. In this way, we keep the number of shader variants needed in check. In total, Impeller has around 50 vertex and pixel shaders and about a similar number of pipeline state objects. To drive home this point, I hacked the renderer to display wireframes instead of filled triangles. If there is anything I want you to take away from this presentation about how Impeller works, it's this very core idea, and the overarching goal of keeping the number of shader variants in check. Now, we still have a few unsolved problems. I glossed over these in the name of simplicity earlier. We need to display a signal of infinite frequency on a discrete pixel grid. This inevitably causes aliasing artifacts. We use MSAA to address those. Let's take a quick overview of this technique. The 2 edges, edge 1 and edge 2, are from different triangles. I've colored them differently. They overlap the same highlighted fragment. The fragment in yellow is shaded, that is, have its pixel shader invoked just twice, once per triangle. This is no different from the case where there is no MSAA. There are n different sample locations within the fragment. In this case, 4, which means this is 4x MSAA. Contributions of each shader invocation are stored at the specified sample location. At resolve time, a filter is run to produce an intermediate fragment color. This addresses aliasing issues. Again, We don't want to invoke fragment shaders any more time in the case without MSAA. So runtime performance is about the same. MSAA does require more storage per fragment for the samples, but this is all in tile memory. So no additional device memory is used unless we explicitly store it across a render pass, which we don't. When discussing anti-aliasing techniques, it is important to take away that we are not using FXAA, that is, rendering to a larger resolution and then sampling down. That would be prohibitively expensive and would also interfere with techniques such as texture sampling. We are only using MSAA to get rid of the jagged edges, that is, geometric aliasing. We don't want this to affect surface aliasing, as this will interfere with the effects of texture sampling. Impeller's offline shader compiler is called Impeller C. All shaders used by Impeller are authored offline. You can browse them in the Flutter engine repository. All the shaders are authored in modern GLSL. We even have the ability to author shaders in HLSL for those on the team more familiar with that shader authoring environment. Impeller C is a two-stage compiler. It first parses shaders in GLSL or HLSL and converts them to SPIR-V. From that SPIR-V, it generates metadata. This metadata includes information about how to feed the shader with data to process. Impeller C generates C++ code that makes this process of feeding the shaders easier and type-safe. The SPIR-V is then optimized for performance. After optimizations, Impeller C then converts the optimized SPIR-V to a backend-specific shading language. This would be the Metal shading language on iOS and Mac, GLSL ES100 on Android devices with the OpenGL ES backend, Vulkan-specific SPIR-V for the Vulkan backend, or HLSL for Direct3D, and WGSL for WebGPU in the future. We have already prototyped converting all Impeller shaders to WGSL if Impeller ever needs a WebGPU backend in the future. Moving all the shader compilation infrastructure offline means that Impeller and the bundled shaders only add about 100 kilobytes of binary size overhead to the compiled Flutter engine. The binary size overhead was also a vital requirement, as moving from the current renderer to Impeller would have been an extremely tough sell if the overhead was about the same as that of the current renderer. Having different engine variants would have also made the transition much harder. Giving developers a gentle on-ramp to Impeller and easing the transition to a new renderer did add a non-trivial amount of overhead to the process. So, shader compilation is done and dusted. Let's move on to other issues. When thinking of performance issues to fix, this note about infrastructure projects comes to mind. We didn't really want to make the existing subsystems 20 or 30% better. At the end of the day, the induced demand just makes bad actors take up the additional overhead, and we are in the same spot we were a few months ago. Instead, let's provide alternatives that reduce the burden on existing overloaded subsystems. Case in point was the use of the stencil buffer for clipping. In Impeller, clipping never uses a save layer. Instead, all clips are affected using the stencil buffer that's always present and uses tile memory. This is very similar to techniques used in games. Now, clips are almost free. This thinking of building new subsystems to alleviate some of the issues often seen in Flutter applications permeates the decision-making process on how Impeller should be put together. On the short-term roadmap, we are focused on making customers successful using Impeller. Hopefully, you have already seen wonders on iOS. We have also migrated some applications developed within Google to Impeller. Given the scope of the transition, helping the very first customers was a high-touch effort, but I'm happy to report that the process of transitioning every new customer to Impeller becomes easier and easier. Sometimes we flip the flag to Impeller and never hear any Impeller-related issues again from that customer. I love it when this happens. Our hope is that this is the norm. I'm happy also to report that Impeller currently implements all renderer operations barring some edge cases. These edge cases are documented on the Impeller project dashboard on GitHub. Operations that conform to a spec like the blend modes should already be identical to the previous renderer. In cases where Impeller has to reverse engineer current behavior, we would love feedback on making the results as close to the previous renderer as possible. Though I should say that they should be pretty close already. We'd like to call the Impeller effort on iOS at 1.0 soon, with the Android effort reaching the same stage a couple of quarters later. To the team, 1.0 means that we are confidently able to recommend that Impeller be the default on the platform. The goal is to be the default everywhere. Longer term, things are a little bit more murky. We would like to explore native 3D rendering scenarios and game engine-like scenarios. We would also love to expose the lower-level Impeller primitives directly to Dart code, usually from multiple isolates. Impeller is already thread-safe. We would love to move more of the renderer to Dart. We would also like to build a libdispatch for Dart backed by Impeller for multi-threaded rendering with the help of Dart. And that's it. You can reach me on GitHub, Discord, Google, or Twitter at Chinmay Garde. It's the same everywhere and boring. So reach out and have a nice day. Take it easy. Bye.